Hi, I am going to teach you how to love physics, and that happens when you learn how to understand physics. The last two videos have focused on kinematics, that is motion where acceleration is constant. First we examined motion with zero acceleration, then we explored motion with non-zero constant acceleration. The problem in those two videos were only constructed to deal with one dimension. The next level of complexity comes when a particle's motion involves both dimensions. Recall how we treated the vectors of position, velocity, and acceleration in one dimension. Remember that a vector is uniquely determined by its magnitude and direction. So to get our hands on those three vectors, we had to determine both the magnitude and direction of each vector. Now in one dimension, there are only two directions a vector may point, left or right in the horizontal, up or down in the vertical. So a simple sign convention was sufficient to differentiate between the two directions found in one-dimensional problems. But think about how direction is specified in two dimensions. It is done by an angle from the horizontal. This is quite different than mere sign convention, where you only have to decide between positive and negative. So how will we approach kinematics in two dimensions? The answer is to simplify. We are going to take the formalism of vector components to turn a complicated two-dimensional problem into two simple one-dimensional problems. So let's do it. A baseball is hit and leaves the bat with a velocity of 40 meters per second at an angle of 35 degrees above the horizontal. Ignoring any possible effects of air resistance, how long is the ball in the air and how far away from home plate does the ball land? First question is, what equations are valid to the situation? Well, this problem involves a constant acceleration, the acceleration of gravity, 9.8 meters per second squared down. So the four kinematic equations used previously are valid. We are given initial velocity and acceleration, so perhaps we could try substituting them into one of the equations and see if anything pops out. But before that, we must deal with the complexity of two dimensions. Remember that any vector can be broken into components. We will convert the initial velocity and acceleration of this problem into their respective component forms. Recall that the y component of a vector is the magnitude times the sine of the angle above the horizontal, and the x component of a vector is the magnitude times the cosine of the angle. So the x component of the initial velocity is 33 meters per second, and the y component is 23 meters per second. The acceleration is completely in the negative y direction, so its x component is 0 meters per second, while the y component is the entire magnitude, negative 9.81 meters per second squared. Notice that if we had been given an unusual field that produced a constant acceleration at some angle not parallel to the vertical, this could be dealt with by taking components of the acceleration just like we did with velocity. Now the acceleration in the x direction is constant, so the kinematic equations are valid in the x direction. Similarly, the acceleration is constant in the y direction, so the kinematic equations are valid for both the x and y dimensions. So we can set up two sets of those equations, one for the y components of all the vectors and one for all the x component of all the vectors. This is what I set up earlier about setting up two one-dimensional problems. Notice that both sets are functions of time. So what we have is two sets of coupled equations. The x and y components of both velocity and position change as time indexes forward, but is the same time in both equations. The main simplification comes from the fact that since both sets of equations involve only one dimension, the directionality can now be incorporated into each problem individually simply by sign convention, just like we did in the previous one-dimensional examples. Now we are at the step where we can start to substitute the numerical values into the equations. The two unknowns we are solving for is the time in the air, that is the parameter t, and the distance away from the home plate where it lands, that is the x location at time t. We are given initial x velocity 33 meters per second And since the acceleration in the x direction is 0, the x velocity at any time t is equal to the initial. Setting the origin at the point the ball begins its trajectory makes the initial x position 0. Since acceleration is 0, the x position at time t simply equals the initial x velocity, 33 meters per second, times time. The y equations are slightly more complicated since the terms for acceleration remain. The y velocity at any time t equals the initial y velocity, 23 meters per second, plus the acceleration, negative 9.81 meters per second squared, times time. The y position at any time t equals the initial y position, 0, plus the initial y velocity, 23 meters per second, plus acceleration times time divided by 2, which is 4.9 meters per second times time. We need the time the ball is in the air and the distance away from the origin it lands. So we need the x-coordinate that corresponds when the ball hits the ground. And that time corresponds to the position at that point. Equation 1 gives no information because it is simply an identity. Equation 2 has both the unknowns we are looking for. Now, since it's the only equation we have that has the final x position, we should be able to solve for the time in one of the other equations and substitute that value back into equation x2 and solve for the distance we want. In both the y equations, there is one more unknown in addition to time. In order to solve for time using equation y1, we must know the final y velocity. In order to solve for time using equation y2, we must know the final y position. Though neither quantity is explicitly mentioned, careful intuitive inspection of the problem reveals both of these data. This is a skill you want to get good at. You want to be able to identify what quantities you can gather from the information given implicitly. In this case, we can implicitly determine what the final y position is. We are told to find something out about the ball when it hits the ground. It hits the ground only when its y position is 0. So the final y position is 0. We also know the final y velocity. Recall the discussion on the last video. At every point in a trajectory like this, the particle will pass through every y position twice. At each point it will have the same magnitude of velocity because the acceleration is the same going up as it is going down. Just the sign will be different. So the velocity at the final position when the ball returns to the ground is simply the opposite that what it was when it was going up. The final y velocity is negative 23 meters per second. So now, from implicit investigation of the problem statement, we have identified the final y position and the final y velocity. Solving either equation y1 or y2 for time gives the same answer of 4.7 seconds. Substituting that into equation x2 gives a final distance of 155 meters. I hope this demonstrated the value of understanding the component forms of vectors. You have to learn to be flexible and use all the tools in your arsenal to rework problems until they are simple enough to solve. Well, if you have any questions, just leave them down below.